Alright guys, in this video we're going to discuss the concept of radioactive decay. So just as a quick refresher, we've covered what makes an atom radioactive. And we said that when you have way more neutrons than protons in an atom, that makes the atom radioactive. And remember that synonym that we learned for radioactive was unstable. And we showed that little animation where the atoms were just shaking because they were so unstable. And the analogy here is when an atom is really unstable, which we call radioactive, it wants to get rid of some of that stress. It wants to release it. Just like when we're really stressed, we want to get rid of some of our stress. Atoms do that too. And so the way they do that is by releasing what is called decay. Okay? And what always happens when this occurs, here's a radioactive nucleus, okay, because we have protons and neutrons in here. The electrons aren't shown. If this atom is radioactive, it's unstable. And whenever an atom is radioactive, unstable, it's going to release some type of particle, which is the decay, and it's always going to give off some energy. And we'll talk about how that energy that's released can have a lot of impacts and a lot of effects on the environment and health and whatnot. But the main thing to know is when a radioactive atom decays, it releases a particle and a bunch of energy. And there's three types of decay that we're going to learn about. The first type of radioactive decay is called alpha decay, and this is usually abbreviated with a alpha symbol from the Greek alphabet. The second type of decay is beta decay, which is abbreviated with a capital B from the Greek alphabet. And the third type of decay is called gamma decay, which is the Greek symbol for gamma is this little kind of Y-looking thing. The main thing to know about these three types, first we're going to get into detail on these two. We're going to save gamma to talk about as a class. But out of these three types, gamma is the most energy. It has the most energy, and alpha has the least amount of energy. So these increase in energy from alpha to beta to gamma, which means we're going to have to take different precautions to protect ourselves from those types of decays, and different materials will block each one of those. So let's first talk about alpha decay. What happens when an atom undergoes alpha decay? So here's an example of an atom that undergoes alpha decay. It's Am241, and we have an arrow here decaying into Np237 and releasing an alpha particle. Each one of these blue and red spheres represents a nucleus. So let's first look up Am241. So if we look at the periodic table, Am is americium, okay, which is down here, element 95. So we want to translate this into an equation. So americium, Am, and remember we write the mass in the top left corner, this is the mass, and 95, because that's its atomic number in the bottom left, is going to decay. Just like any chemical reaction we've talked about before, you're just starting with something, it's the only kind of reactant, and it's decaying into something else. It's decaying into Np237. So let's look up Np on the periodic table. Here it is, neptunium, which is an atomic number of 93. So we're going to write 93, neptunium, and the mass is 237. Notice, I took the mass that was given in the atom listed, the isotope listed, not what is listed on the periodic table. Okay, so there will be a mass listed on the periodic table. Don't list that. List the one that is in the problem. But something else is also released, this alpha particle. So something else has to be released. What is this alpha particle? So remember, the conservation of matter tells us the mass of what we start with has to equal the mass of what we end with. Where are our masses? Our mass is 241 here. Here's 237. So we can kind of see essentially that our total mass started as 241. So that means our total ending mass has to equal 241. We already have 237, so the mass of this extra particle must have a mass of 4, because 4 plus 237 equals 241. Let's do that same logic with the atomic number. The atomic number here is 95 for americium. That has to be equal to the atomic number of neptunium, 93, plus the other atomic number. So the atomic number for this must be 2, because 2 plus 93 equals 95. Now, I got to figure out what element this is. Element 2, periodic table. If I check the periodic table, the atomic number of 2 is helium. So I'm going to write the name of this element, which is He. So what we've just done is we've written an equation for the alpha decay of americium-241. What are the things to know about this? Number one, this atom of He, this is what we call an alpha particle. So if you remember Rutherford's gold foil experiment, when he was firing alpha particles at the thin foil, he was actually firing helium atoms, little atoms of helium. So when an atom undergoes alpha decay, it releases an atom of helium with a mass of 4. So that's the first main thing to know. Okay. The second thing to know is this reaction follows the conservation of mass. So whatever you start with, the mass has to equal what you end with. There's two other vocabulary terms we need to know. Okay, and I'm going to highlight those here in pink. The isotope that you start with, what's on the left side of the arrow, okay, this is called the parent isotope. Okay. The isotope that you end with, not the alpha particle, but the isotope that you end with is what's given off, what's released. It's the product of this compound, of this isotope, and it is called the daughter isotope. So the vocab words you need to know: parent isotope is what's on the left of the arrow, the daughter isotope what's on the right side, and the alpha particle. Another common question students ask is, does it matter if I list this one first or this one? It doesn't matter. I could switch them. I could have, the helium atom written here and neptunium written here. It's the same thing. It's the same thing. Alpha decay, the energy that's given off is dangerous, okay? But alpha particles can be stopped with like a piece of paper. Okay, a piece of paper is enough density to block an alpha particle, prevent it from affecting your body or somebody else. So here's the type of example problem you need to do. Write the reaction for the alpha decay of uranium-235. So the first thing I notice in this problem is I see that it says alpha decay. So that keys me into what the particle that's going to be released is. I know that an alpha particle is 4He2. It's an atom of helium. And I'm running the reaction for the alpha decay of uranium-235. So that keyword of tells me that this is going to be the parent isotope. This is what I'm going to start with. So now I need to translate this into a reaction. So uranium-235. Since it's the parent, it's going to be on the left side of the arrow. I need to look up its atomic number though. So I go to the periodic table. I check that uranium here has an atomic number of 92. So uranium-92. I know this is alpha decay, so I'm going to have an atom of helium. So I'm just going to go ahead and write that down here, 4He2. Now I got to figure out what's left. So I use my idea of conservation of matter. So the mass of 235 equals 4 plus something. So that something must be 231, because 231 plus 4 equals 235. Do the same thing with the atomic number. 92 equals 2 plus something, so that something must be 90. I look at the periodic table to find element 90, and I see that it's thorium, Th. So I'm going to go ahead and write thorium, Th. Here is my reaction for the alpha decay of uranium-235. You don't need to show these equal signs and circle all this stuff. I was just doing that to emphasize how we were solving the problem. So if you wanted to clean it up, you can go ahead and do that too. But that's how we would write a reaction. And just to remember, this is the alpha particle right here. This is my parent isotope, and this is my daughter isotope. Next one, beta decay. So beta decay is a different particle that's released, even though energy is still released. So let's do the same thing. This is an example of an atom undergoing beta decay. Let's translate this image into an equation. So I have H3. So H, I know, is the element hydrogen on the periodic table. So hydrogen is H. It has a mass of 3. And if I check the periodic table at the bottom is the atomic number of 1. Then arrow, this is going to produce helium-3. Okay, so He with a mass of 3. Helium has an atomic number of 2. Okay. So now I got to figure out what's going to be left. So, well, 3 equals 3 plus something. Okay, well that number has to be 0. And then 1 equals 2 plus something. So this number has to be a negative 1. Because negative 1 plus 2 is equal to 1. Or just think of it this way. 2 minus 1 is equal to 1. So what is the name of a particle that has no mass? The name of a particle that has no mass is an electron. So we'll just abbreviate that with an E. So in beta decay, an electron is released. The reason we write it with a negative 1 is because what happens is a neutron, which is here in blue, gets turned into a proton. Notice how there's 2 red spheres here and there's only 1 here. So 1 proton, now we have 2. So this negative 1 just represents the change in that. It's not that an electron actually has negative 1 protons. We just have to do it to balance the conservation of matter. So here is our reaction for beta decay. The other things to know, as usual, what you start with is called the parent isotope. What you end with is called the daughter. And then an electron is the key thing you need to know for beta decay. Now, beta decay has more energy than alpha decay. It's more dangerous. It has more energy when it's released. What can stop beta decay? It can go through a sheet of paper. You need some type of metal to block it. Okay, so you need like a thin piece of foil, like aluminum foil will block beta decay. But beta decay will go through a sheet of paper. So if you had this electron shooting off, and here's a piece of paper, it would go right through it. But if you had a piece of foil, it would get deflected off. So you could protect yourself from beta decay with a sheet of foil. So let's do a practice problem. Write the reaction for the beta decay of nitrogen 14. Okay, so first thing I see, this says beta decay. So I'm going to recognize right away in my equation I'm going to have this particle, 0e negative 1, an electron. And I also see that I'm using nitrogen 14 of, so this is going to be my parent. So let's go ahead and write that out. So nitrogen with a mass of 14. Check the periodic table for the atomic number of nitrogen. It's 7. Since it's the parent, I'm going to draw an arrow. Now I'm just going to take this beta particle, I'm going to write it in right here, 0e negative 1. And what's going to be left? Okay, well 14 is equal to 0 plus something, so the mass is still going to be 14. And 7 is equal to negative 1 plus some number. So this has to be bigger than 7. 8. And if I check the atomic number on the periodic table of 8, it's oxygen. So this would be the reaction for the beta decay of nitrogen 14. You want to know the most common mistake that students make? Common error is they just take these numbers and they do 7 minus 1 to get the atomic number of 6 here. That is wrong. Don't fall into the trap of whatever you start with in the parent, you just subtract. Think of it as an equal sign. 7 is equal to negative 1 plus a number. 7 is equal to negative 1 plus x. So if you thought of it algebraically, to get x by itself, add 1 to both sides. So you would be left with x equals 8. That's how we arrived at this. So watch out for that trap. Let's do one more practice one together. An unknown parent isotope undergoes alpha decay to form neon 22. What is the parent isotope? Okay, so let's break down what the problem is giving me. It's saying an unknown parent isotope. what is the parent isotope? So I don't know what's going to be on the left side of the arrow yet. I know that it undergoes alpha decay. Okay, so that's a helium atom. So I know that's going to be given off. So I can write that over here on the right side. And it's going to form neon 22. Think of the word form as an arrow because you're making it. So it has to come after the arrow. So neon 22, 22 Ne, check the periodic table. The atomic number is 10. So now in this problem, I'm kind of working backwards. But the idea is still the same. Think of this as an equal sign. 22 plus 4 has to be equal to some number. Okay, 22 plus 4 is 26. 10 plus 2 is 12. So I check the periodic table for the atomic number of 12, and that is magnesium. So boom shakalaka. Here is the reaction that's going on, described in the problem. But let's think about what it's asking for. It's asking for the parent isotope. So I would just want to make sure or label this. Parent isotope is magnesium with a mass of 26. So it doesn't matter that this mass doesn't match what's on the periodic table. Remember, we've learned now that there's isotopes. Don't fall into that trap. Don't look at the mass on the periodic table. Look at what's given in the problem. The last thing to note is about gamma decay. Okay. Gamma decay is the most dangerous decay. It has the highest energy. Okay. There is no equation for a gamma reaction because gamma decay just gives off energy, a ton of energy. Common ways that we see gamma decay are actually like in X-rays. An X-ray is just a release of gamma decay. Okay, it's really high energy. So gamma decay can go through, like if this is paper, and if this is foil, gamma decay can go right through that stuff. The only thing that can really stop gamma decay, I'll make this like 3D here, okay, is thick lead, sheets of lead. Okay, so that's why when you go to the dentist, for example, and you get an X-ray of your teeth, or if you've ever gone to the X-ray, get an X-ray at a hospital, they put that big, heavy apron on you. It's filled with thick lead because the X-ray is gamma decay, and they want to protect you from it. So this would deflect off, boom, that would block gamma decay. We've covered all three. Let's get some practice together.